Hello everyone, welcome to EEEE lecture number 5. Today we are going to discuss on nodal analysis using Kirchhoff's current law, that is KCL. So before beginning with the steps, let us take an example and understand. So let's say this is a circuit given to us and we need to apply nodal analysis. So first of all, we have to define the nodes. So let me use red color to define the nodes. So last lecture we have seen what is the definition of a node. So over here this is my node where one or two elements are connected. So here 6 volt and R1 is connected. This is another node. Alright. This is another node and this is another node. Alright. The next step is once we define, we define the variables on these nodes now. So this is, let's say, V1, V2, V3, V4. Alright. So this is my node number 1, node number 2, node number 3 and node number 4. Alright. Also we need to define the ground node. So all these points over here are connected, are one and the same nodes. These are one and the same. So this is my reference node. Alright. Now we have defined the variables V1, V2, V3, V4. We can also define it as VA, VB, VC or VD to indicate the voltages. Alright. And now we need to apply the KCL at each node to obtain the equations associated with that node. That we will see when we solve a numerical. But there is one more thing which we have to see over here. So if a voltage source is connected between a node and a ground directly, then the voltage at that node is equal to the voltage of the source. For example, over here, in this case, we have this 6 volts source directly connected between a node and a reference node or a ground. So we can say that my voltage V1 is equal to 6 volt. Alright, please remember this. So if a node is directly connected, if a voltage source is connected between a node and a ground, then the voltage of that node will be equal to the voltage of the voltage of the source. Similarly over here, here we have 4 volt source, voltage source which is connected between a node and a ground. So over here V4 with respect to ground will be minus 4 volt. Okay, so this is very crucial to understand before going for applying KCL at each node. Alright, so these two steps are very important. I hope it is clear now. Now let's see another concept, another example we can see. So let's consider this circuit. So here also we need to apply the nodal analysis. So it's very obvious that the below nodes over here are one and the same. So these are all reference node. So these are my reference node or a ground node. So first of all, we need to define the reference or the ground node. All right. Now I will define the various nodes over here. So this is node number 1, node number 2, node 3 and node number 4. Alright, now we need to define the variables associated with it. So let's say this is V1, V2, V3, V4. Now from the last example we have seen that whenever a voltage source is connected between a node and a ground, uh, the voltage of that node will be equal to the voltage of the voltage source. So this directly V1 is 6 volt. Similarly over here V4 will be, because of this 4 volt voltage source, your V4 will be minus 4. Now there is something else happening over here. So whenever, if a voltage source is connected between two nodes directly, then it's a supernode concept which we need to obtain. Okay, so here as we can see, 12 volt voltage source is connected between two nodes directly. So that means this will form a supernode. So this forms a supernode, and one of the supernode equation will be how to solve this. We need to employ the supernode concept, and in supernode we need to write the equation of the supernode using KCL, and we need to write the equation relating the node voltages and the voltage source. All right, so equation relating the node voltage and the voltage source will be over here. If you see carefully, here we can write the equation relating the node voltages and the voltage source. So because it's a higher voltage. This is positive, this is negative. So V3 minus V2 is equal to 12. So this is the equation which we get by applying the supernode concept, one of the equation, and other equation will be by applying the supernode. So over here we can say node 2 and 3 forms a supernode. All right, so this is the concept which we need to investigate while we solve numericals further. So as you can see over here, node 2 and 3 forms a supernode, and 12 volt voltage source, because the 12 volt voltage source is connected between node 2 and 3. And what is the equation related to it? V3 minus V2 is equal to 12. This is the equation relating the voltages at the supernode. So this is one equation we get. All right, now let's start solving some more numericals, some numericals on nodal analysis and how do we apply KCL to it. All right, so let's start with our first numerical. Okay, so numerical number 1 says that we need to find voltages V1 and V2. So V1 and V2 are defined as follows. So this is my voltage, let me use different color. This is V1 and this is V2 given to you. Okay, this is directly given to you, V1 and V2. We need to find V1 and V2 using nodal analysis. So the first step is already clear. We have already defined the nodes over here. So this is my node 1, this is node 2, and this is my ground node. We can actually connect a ground over here. Okay, so this is my reference node, reference or ground node. Okay, now how do we solve this further? Now let me show it to you. So first of all, we need to apply, we need to direct the currents in particular nodes, right? For example, let's say here, over here in this branch, here the current is flowing into the node, right? So here it is 1 ampere. Okay. Whenever a current is not defined, then we have to define it outward always. So this is my outward current. Let me call it as I1. Okay. Here also I2. So if we apply KCL at node 1, we will get 1 ampere is the incoming current and I1 and I2 are outgoing. So we will get 1 is equal to I1 plus I2. All right. Similarly, here also we'll define outgoing current as I3, and here already a current source is there. So this is 2 ampere. One more thing to note over here is that even if we have a resistor connected in series with the current source, it doesn't matter. The current will remain the same. Okay, so this we need to take care. All right, so let's start solving this numerical. So let me use blue color. So we'll apply KCL at node 1. So when we apply KCL at node 1, what do we get? Incoming current is equal to outgoing current. So 1 ampere is equal to I1 plus I2. So 1 is equal to I1 plus I2. Now we have applied KCL before. So this 1 will be equal to, what is I1? I1 will be V1 minus 0 upon 2. Okay, I is voltage upon resistance. So voltage difference upon resistance, that will be V1 upon 2. I2 will be, I2 is originating from here and it's going towards V2. So V1 minus V2 upon 2. V1 minus V2 upon 2. So that's how we write I2 as in terms of voltages divided by the resistance. All right. So we'll cross multiply and we get the following. So we get 2 is equal to 2 times V1 minus V2. Let's call this as equation number 1. All right. So 2 V1 minus V2 is equal to 2. So that is our equation number 1. All right. Now let's apply KCL to node number 2. So let me use another color. Yeah. So KCL at node 2. Also let me save the document. All right. So at node 2, how many are incoming currents? I2 and 2 ampere are incoming currents. So we can write I2 plus 2, and that is equal to outgoing current, which is I3. So I3 is equal to, outgoing current is equal to sum of incoming currents. All right. Now what is I3 from here? I3 will be V2 upon 1. So this will be V2 upon 1. I2 will be, now I2 is defined in this direction, so it will be V1 minus V2 upon 2 only. So V1 minus V2 upon 2, and this is plus 2. Now here we can cross check and check, this is 2 V2 is equal to V1 minus V2 plus 1. All right. So that is what we get over here. All right. So here we have multiplied by 2 this side. This is actually 4 because we have cross multiplied. So we have multiplied throughout left hand side and right hand side by 2. So we have 2v1 is equal to v1 minus v2 plus 4. So we get minus v1 plus 3v2 is equal to 4. This is our equation number 2. So we have two equations relating the, having corresponding to two nodes. So now we'll check them together and write in a matrix form. So we write over here in the matrix form as follows. So here we write it as v1 and v2, and here the coefficients will come on the right hand side. So here it will be 2 coefficient of v1 and coefficient of v2 will be minus 1. Then this here it will be minus 1 and coefficient of v2 will be 3. And on the right hand side here we have 2 and here we have 4. So kindly solve this equation number 1 and 2 simultaneously using a calculator and calculate the value of v1 and v2. All right. Okay, so the value of v1 is coming out to be v1 is equal to 2 volt and v2 is equal to 2 volt. So these are the voltages what we are getting. All right, so both voltages are equal to 2 volts. So that is the answer. Now let's say if we want to calculate one of the current, let's say I1. So what will be I1? Let's say that for example we want to calculate I of 1. I current through 1 ohm resistance. So I1 will be V1 upon 2. So it will be V1 upon 2. That will be 2 upon 2. That will be 1 ampere. And the current is going down. So we can show the arrow down. This is just for example which we are checking it. Okay. So in this manner it's plain and simple. We write the KCL at node number 1 and node number 2. And there it is. Alright. Now okay, so let's go to LTspice and check this out, whether we are getting similar answers or we are getting something different. All right, so let's do it in LTspice. Let me open LTspice and keep it ready. Yeah, and let me keep this window open with the circuit diagram. All right, so let me build the circuit side by side in LTspice. This is LTspice. So let me open components and I'll first type current. Okay, I have to rotate it, so I'll press Ctrl R. Let me rotate it. Yeah, Ctrl R, and I'll place it over here. Then I require one more, so I'll use this copy option to copy the current source once again. Okay, now I require resistor, so you take the resistor from here and place it over here and over here. All right, if I want to push any component further, I can select it using this move terminal, move option. Okay, now I require two more resistance, so I'll rotate it. Here also I'll rotate it. Yeah, there it is. Now all the components are ready. We need to just connect them together with the wire. So here is my wire. Okay, and I'll join everything as per the given circuit diagram. All right. Okay. So already the nodes have come automatically. So this is node 1, node 2, and my ground node I need to connect the ground also. So here it is. Always do not forget to connect the ground. Now I'll add the values. So this is 1 ampere. This resistance is 1 ohm. Then this resistance is 2 ohm. This resistance is 2 ohm. This is 1 ohm, and that's it. And here this current source is 2 ampere. All right. Now I need to define the voltage over here. This is, let's say, node number 1. Okay, let me just cancel this out. Yeah, right click on label net, and I call this as 1. Okay, node number 1, and this is node number 2. I right click and change it to 2. Alright, and now I'll go to simulate, click on run, and then click on DC operating point, then click on OK. So here it is. I'm getting at node voltage 1, V of 1 is how much? 2 volt. That is what we are getting over here. See, V of 1 is 2 volt and V of 2 is also 2 volt. Alright, okay. So in this manner, we can verify the current very easily, and also I mean the current or voltage is present in a linear network very easily. So V1 and V2 are 2 volt. Also the current I1 is flowing through 2 ohm resistance. So current I1 is this, here it is I R1. So I of R1 is 1 ampere, as you can see clearly. Okay, so yeah, so it's showing perfect answers, LTspice. All right, so let's go to the next numerical now, and let's apply nodal analysis again and find out the answers. All right, so numerical number 2, it says that we need to calculate the current flowing through 5 ohm resistance by nodal analysis. So many times we need to find the current flowing through a particular element. In this case, it is the current flowing through 5 ohm resistance. So let's apply. So here I'll mark the current flowing through 5 ohm resistance as I phi. Okay, 5 ohm. Alright, so here the first step will be to define the ground node or the reference node. So here is my, all these are nodes connected together, one and the same. So this is my reference node. So I have defined my reference node. Now I'll define the other nodes. This and this point are the same. So this is my node number 1. This is my node number 2. And this is my node number 3. So I'll define 3 voltages as V1, V2 and V3. Now I have to define the currents. So current, I can define it over here. This is the outgoing current of, actually this is 4 ampere. Here also I'll define it as outgoing. This is I1. Here also outgoing as I2. Now current flowing over here, I'll define it as I3. Current flowing over here, I'll define it as I4. Current flowing over here, I'll define it as I phi. Now notice one thing, all the currents which have not been defined, I've defined as outgoing only. Okay, so that's the practice which we need to follow. And this is incoming current to node 3 as 8 amperes. Alright, now we have to patiently apply the KCL at node number 1, node 2 and node 3 and get the equations and then get the answer directly. Alright, so let's start applying. I'll write over here KCL at node number 1. Okay, so let me please concentrate on this diagram. So which are the incoming currents? None of the currents are incoming, all are outgoing. So we have 4 plus I1 plus I2 is equal to 0. Okay, so we write over here 4 plus, what is I1? I1 will be V1 upon 2. V1 minus 0 upon 2. So it will be V1 upon 2 plus, what is I2? V1 minus V2 upon 3. Okay, so it will be V1 minus V2 upon 3, and that is equal to 0. Now don't try to do LCM, just as it is divide them and write in fraction. So that means 4 plus V1 upon 2 will be 0.5 V1. 1 upon 3 is 0.33. So 0.33 V1 minus 0.33 V2 is equal to 0. All right, and now solve this. So you'll add this and this. So you'll get 0.833 V1 minus 0.33 V2 is equal to minus 4. So this becomes our equation number 1. All right, so one advice is don't try to do LCM, write in fraction form like this only. Okay, next we apply KCL at node 3. Okay, so let me use a different color. This time I'll use green. So KCL at node 3. So this is my node 3. So I have I phi as the outgoing current and I4 and 8 as the incoming current. So I'll write I4 plus 8 is equal to I phi. Now what is I4? I4 is, see, starting from V2 ending at V3. So V2 minus V3 upon phi, V2 minus V3 upon phi plus 8. And what is I phi? I5 is V3 minus 0 upon 4. So it's V3 upon 4. Now as again as usual, solid in fraction only. So V2 upon 5 will be 0.2 V2 minus 0.2 V3 plus 8. 1 upon 4 is 0.25. So 0.25 V3. Okay. So now we add them together. So here we'll get uh, 0.2 V2 minus 0.45 V3 is equal to minus 8. So this becomes equation number 2. Alright. Okay. So very calmly write down the equations without any disturbance. Now we'll apply KCL at node number 2. So let's use black color only. So KCL at node 2. So at node 2, if you look carefully, I2 is the incoming current and I3 and I4 are outgoing current. So we can write I2 is equal to I3 plus I4. So I2 is V1 minus V2 upon 3. I3 is, if you look carefully, I3 will be V2, here you're going from minus plus. So V2 plus 20 upon 2. Okay, did you understand? So here we have a 20 volt voltage source. So it will be V2 plus 20 upon 2. So V2 plus 20 upon 2. And I4 will be V2 minus V3 upon 5. So plus V2 minus V3 upon 5. So let's solve this. So here we'll get that is 1 upon 3 is 0.33 V1 minus 0.33 V2. Yeah, then we'll get equal to 0.5 V2 plus 10 plus 0.2 V2 minus 0.2 V3. Alright. So if we club the terms together, we'll get that is 0.33 V1 minus we club the term of this V2, this V2 and this V2 together. So 0.7 plus 0.33. So it will be 1.03 V2 plus here we'll get plus zero point 0.2 V3 is equal to 10. So this is equation number 3. So we have three nodes. We have applied the KCL at node number 1, 2 and 3, and now we'll write solve 1, 2 and 3 simultaneously. Okay, so we'll write solve 1, equation number 1, 2 and 3. Okay, and here we write it in a matrix form. Okay, that will be easier to add it in the calculator. So for the matrix form, we write the first equation as this is V1, V2, V3. Okay, and the coefficients over here are minus 4 first. It will be 0.833. This is V1 coefficient minus 0.33 and V3 coefficient is 0. Okay, the second equation is V1 coefficient is 0 and V2 coefficient is 0.2 and V3 coefficient is minus 0.45. So it is minus 0.45. Okay, so I think I need to write a little bigger this one. So minus 0.45. Okay, and your other coordinate is minus 8. All right, here we have 0.33, the coefficient of I1, then minus 1.03, and here we have 0.2, and on the right hand side we have 10. So this is what we get. Let me write this a little bigger. Okay, now we need to solve this in your calculators. So please kindly solve this and check the answers. We are getting V1 as, let me write over here. V1 has come out to be minus 8.76. V2 has come out to be minus 9.92. And V3 is coming out to be 13.37. So that's the answers what we are getting. Alright, we got all the node voltages. Now let's go to the question. We need to find current through 5 ohm resistance. So current through 5 ohm resistance will be I 5 ohm will be V2 minus V3 upon phi. So current through 5 ohm resistance will be, we can write over here, V2 minus V3 upon phi. That will be minus 9.92 minus 13.37, I mean minus, okay, and divided by phi. So what do we get? We got 4.65 amperes. All right. So it will be minus 4.65 amperes, and the current direction will be like this. Okay. Now if I want to write this as plus, I'll write equal to 4.65 amperes, and the direction will be opposite. Okay, so we can write the current, we can change the direction of the current and write it as positive. So current flowing through 5 ohm resistance will be minus 4.65 in this direction, going from left to right, or plus 4.65 going from right to left. All right, so this is how we can solve a numerical on the nodal analysis. All right, okay, so this is numerical for your home assignment. So here we need to find the current flowing through 10 ohm resistance. So this is the 10 ohm resistance, current flowing through 10 ohm resistance. So this, I'll give you the hint, okay, and then you need to solve on your own. So the hint is, you first of all identify the nodes. So here the nodes are this one, this is node number 1, this is node number 2, and this is node number 3. All right. So, and this is my reference node. This is my reference node. All right. Now we have to be very careful in writing the equations. All right. We have to define next the current directions. Okay. So we can define the current directions as follows. So here I can define the current down. So this is I1, this will be I2, and this will be I3. Next, I can define the current direction over here as I4, and this current direction will be I5. And over here, I'll define the current as I6. All right. Now we need to apply KCL at node 1, node 2, and node 3, and you will get the equations in terms of V1, V2, and V3. So find V1, V2, and V3, and finally I of 10 ohm will be V1. I mean, here we can define the voltage V1, V2, V3. So I 10 ohm will be V1 minus V3 upon 10. All right. So this is what we get. So let me write down the values of V1, V2, and V3 so you can cross check it. So V1 came out to be 15.944 volt. Okay, these are the answers. V2 came out to be 4.316, and V3 comes out to be 0.2652. All right. So these are the values of the node voltages, and finally the current flowing through 10 ohm resistance will be 1.62 amperes. So let's do one thing. Instead of analytical solving it, let's solve it in LTspice. So let me take another schematic and let's try to solve this in LTspice. Okay, so let's go to component and type over here voltage. So I'll add a voltage source over here. I require one more over here, so add it like this. Okay, now I'll add the resistor. I'll rotate the resistor and add two resistors over here and over here. Let me quickly complete the circuit, and I require one more resistor over here. Okay, so yeah, all the components are ready. Now I need to connect them together with a wire. So let me do that quickly. All right. Now I'll connect the other components. Okay, and define the ground node also. So this is my reference or the ground node. I'll connect it with a wire. All right. Now I'll define the values. So this is 25 volt, 25 volt. This resistance value is 4 ohm. This resistance value is 2 ohm. This resistance value is 3 ohm. This will be 7 ohm. I'll right click and change the value. So this is 2, this will be 10, and this voltage source will be 12 volt. All right. Now I'll define the node voltages as 1. Here it is 1. This will be 2, and this will be 3. Let me change it to 2 and 3. All right. So I need to find V1, V2, and V3 first. So I'll go to simulate, click on run, and select DC operating point, and click on OK. Okay. I'll get the value of V1, V2, and V3. So V1 came out to be 15.944, and that's what we get. Then V2 came out to be 4.3156. So 4.316, it's correct. And V3 came out to be minus 0.2652. All right. So it's coming all right. Now I'll get the current flowing through 10 ohm resistance. So that will be R6. So current flowing through R6 is coming out to be negative, but don't worry, it's not negative in fact. Okay, so why it is not negative? Because the current flowing out of the voltage source in LTspice is considered as negative. So we are getting minus 1.62, but that is fine. I'll show you how to get it proper current. So we just cut this wire, okay, and add a 0 volt voltage source. So I'll add it a voltage source over here. Let me add it like this. All right, and let me connect it. If you add a 0 volt voltage source, it won't affect the circuit, but this 0 volt voltage source will act as an ammeter. So now current flowing through I3 will be same as current flowing through R6. So current flowing through V3, now we'll find out. Here it is. Current flowing through V3, as you can see, it's plus 1.62, and that is the answer actually. Current flowing through this voltage source, 0 volt voltage source V3 will act as a current meter. So 1.62 is the correct answer. All right, and not the minus sign. So this is how you can check, the various currents and node voltages using LTspice, and it's very accurate. All right. Now, this you can solve it on your own now. All the answers were simulated in LTspice and checked. Now let's go to numerical number 4. All right. Now numerical number 4 is very important. All right. You will understand in a minute why. So, first of all, we need to identify the various nodes. So here I'll identify node number 1. This is node number 1. This is node number 2. This is node number 3. Okay. And this is my reference nodes. These are all my reference node. So I'll write over here, this is my reference node. Now wait a minute. Before going any forward, here we have a 20 volt voltage source connected between two nodes. So here it is a concept of a supernode. So we can start by writing over here that node number 2. So the first point is that node number 2 and 3 forms a supernode. So first write down the node voltages. This is V1, V2, and V3. So immediately we can write the equation of the supernode as in terms of the node voltages as. So here we have plus minus. So will V2 minus V3 is equal to. So here we can relate it as follows. V2 minus V3 is equal to 20. So V2 minus V3 is equal to 20. Let's call it equation number 1. All right. Now, supernode means we need to, this entire thing, we highlight it. Okay. Now we apply KCL to the supernode. So KCL to the supernode will be, okay, any current entering this nodes V2 and V3, except for V2 between current between V2 and V3. So what I mean is, first let us define the currents. So here is incoming current, this is 10. This is outgoing as I1. This is I2. Okay, this is I2. We cannot define any current between the voltage source. So we can define the current over here. This will be I3. This will be I4, and this will be I5. Okay, so let's apply KCL at supernode. So KCL at supernode. So how will apply? So don't apply KCL, the current, don't define the current in between the nodes 2 and 3, but we can define the currents coming into the node 2 and 3 individually. All right. So let's check at node number 2. So we have incoming current as I2. All right. And here we have outgoing current as I3. Okay. So we can write over here. Okay. So here we have at V3 also we have outgoing current as I4. And now here outgoing current is I5. So here all the outgoing currents are I3, I4 plus I5. And incoming current is I2. So that is equal to I2. So this is my KCL at supernode. Okay. So you treat this both the nodes and one node only. Okay. So what are the currents which we have written over here? I2 is the incoming current, I3 outgoing, I4 outgoing, I5 outgoing. So this is how we can define the currents. And now it's very easy to write the currents. So I3 will be V2 upon 1. I4 will be V3, here it's plus and minus, V3 minus 10. So it will be, oh, sorry. I guess let me cancel it out. Okay, wait a second. Let me clean this out. Okay, let me save it also. All right. So let me write this again so that it will be clear. So this is my reference node. Let me connect my pen tablet once more. All right. Okay. Wait a second. I'm reconnecting my pen tablet. Okay, it's all right now. So let's start. So this was my reference node. All right. And now let's write down the KCL equation at the supernode. So we can write KCL at supernode gives the following. So supernodes are V2 and V3. Treat them as one node only. Okay. So we have incoming current I2. Let me reconnect my pen tablet again. It's not that smooth. Okay. So I2 will be equal to all the outgoing currents I3 flowing out of node 2, I4 flowing out of node 3, and I5 also flowing out of node 3. So it will be equal to I3 plus I4 plus I5. All right. Okay. Now what is I2? Let me save this document. Okay. So what is I2? Basically, I2 will be current flowing through V1 and V2. So it will be V1 minus V2 upon 2. I3 will be V2 upon 1. I4 will be V3 upon 5. No, it will be V3 upon 5. No, V3 minus 10 upon 5, because there is a voltage source, and why minus? Because it is going from plus to minus. And then I5 will be V3 upon 2. Understood this? I'm going very slow over here because we are applying the KCL at the supernode, and that needs to be understood. All right. So now let's do it forward. So that is, this is zero point 0.5 V1 minus zero point 0.5 V2 is equal to V1 plus, let me open the document again. Okay, no, it's slightly behaving weirdly. All right. Okay, let's hope it works fine now. So this will be 1 upon zero point 0.5. That will be zero point 0.2 again. So this is zero point 0.2 V3 minus 10 upon 5 will be 2 plus 0.5 V3. Now I'll club all the terms together. So that is zero point 0.5, and here we have 1. So it will be minus zero point 0.5 V1 plus this is minus zero point 0.5, and here we have, yeah, V2 also. So this is V2. This is V2. Oh, sorry. This is V2. Okay. So what do we have over here? This is zero point 0.5 V1. I mean plus zero point 0.5 V1. Oh, sorry again. I guess there is some previous writings which are coming into picture. Let me quickly rewrite it, erase it and write it again. Very sorry for this. Let me save this document first. Okay. So previously I have written some equations. Okay. I have colored it with white color. So that's why it's appearing again whenever I use a eraser. All right. So let me, write it again. No problem at all. We are revising, just, writing the equation at the supernode. So again, I'm writing at supernode. The equations will be currents flowing through the node 2 will be I2 will be the incoming current. Outgoing current is I3. And then at node 3, outgoing current is I4 and I5. So plus I4 plus I5. So very simply we have written it. Okay. Now next I2 will be um, V1 minus V2 upon 2. I3 will be V2 upon 1. I4 will be V3 minus 10 upon 5, and I5 will be V3 upon 2. Alright, so we have very plainly written it, and now we'll write over here as, let me maximize this part. This will be zero point 0.5 V1 minus zero point 0.5 V2 is equal to V2 plus 0.2 V3 minus 2 plus zero point 0.5 V3. Okay, don't solve it by LCM, solve it like this. So here we club the terms together. It will be 0 0.5 V1 minus 1.5 V2, then minus zero point 0.7 V3 is equal to minus 2. Alright, this we call it equation number 2. Okay, got it? So this is what we happens when we apply KCL at supernode. And now we apply normal KCL at node 1. Okay, so we need not apply any supernode. Node 1 is not a supernode, not a part of a supernode. So we'll apply KCL at node 1. So what happens when we apply KCL at node 1? Node 1 we get incoming current is 10. So 10 is equal to, outgoing currents are I1 and I2. So 10 is equal to I1 plus I2. So 10 is equal to I1 is V1 upon 3 and I2 is V1 minus V2 upon 2. Alright. So we'll write over here, this is 1 upon 3 will be 0.33 V1. 1 upon 2 will be 0.5 V1 minus 0.5 V2. Now we club the terms together, so we'll get 0.8333 V1 minus 0.5 V2 is equal to 10. This is equation number 3. Alright, so we have the three equations. So let's solve them simultaneously together. So we can write solve equation number 1. Oh, sorry. Again, I guess this overwriting is coming. Sorry for that. Okay, so let me wipe that out. Very sorry for the overwriting part. So whenever I use the eraser, it pops up. So let me quickly wipe it out. Okay, I think it's fine now. And let's not use the eraser now. Let me use the green color and complete this part again. So we apply KCL at node 1, 10 equal to I1 plus I2. So 10 equal to, let me rewrite it quickly. So V1 upon 3 plus I2 is V1 minus V2 upon 2. Alright, so we get 10 equal to 0.33 V1. Here we'll get 0.5 V1 minus 0.5 V2. So we get 0.833 V1 minus 0.5 V2 is equal to 10. So this is our equation number 3. So we got 3 equations now. So let's solve this 3 together. So we'll write solve equation 1, 2 and 3. So we get, so we need to do that in calculator now. We need to take help of the calculator. So let's write this equations in the matrix form. So let me write it over here. So write over here V1, V2, V3, and then here the coefficients will come. Equation number 1, we have a coefficient of V1 is 0, V2 is 1 and V3 is minus 1. So 0, 1, minus 1, and right hand side we have it as 20. So that is equal to 20. Alright. Next equation is equation number 2. We have 0.5 minus 1.5 minus zero point 0.7 is equal to minus 2. Alright. Then equation number 3, the coefficient of V1 will be 0.8333. Coefficient of V2 is minus zero point 0.5 and coefficient of V3 is 0. Alright. And here we have on the right hand side 10. So solve these equations simultaneously, and what you will get is as follows. You'll get the value of V1 as, let me write it down over here. Okay, V1 will come out to be 18.94 volt, V2 will come out to be 11.57 volt, and V3 will come out to be minus 8.42 volt. So please cross check these answers. And finally, um, after finding the node voltages, what we need to find is current through 5 ohm. So current through 5 ohm will be, here it is I4 actually, V3 minus 10 upon 5. So current through 5 ohm will be V3 minus 10 upon 5. V3 is minus 8.42 minus 10 upon 5, and that comes out to be minus 3.684 ampere, and the current direction is going from left to right. Here it is. Okay, from top to bottom actually. Current direction is from top to bottom and not this. All right. Let us not use a eraser. Okay. So it's from top to bottom. So that is the answer which we get, and this is very important in terms of learning the supernode concept. All right. I hope the answers are you're getting the answers. Now let us not solve this in LTspice, and let us solve numerical 5 in LTspice and check the answer instead. Okay. So let's come to numerical number 5. This is the last numerical for today. So we need to find the current through 2 ohm resistance, 8 ohm resistance, 6 ohm resistance and 4 ohm resistance. In fact, find the current through all the resistance in the circuit. Okay. So first of all, we need to define the nodes. So let me define the node over here. So this is node number 1. I'll call the voltage as V1. This is node number 2, voltage V2. This is node number 3, and I call the voltage V3. Alright. And this is my reference node. These are my reference node. I'll connect it to ground. Alright. Now I need to define the current direction over here. So first of all, my current direction, I'll define the current direction over here as follows. So let us start with this current direction. So I'll start over here. Current, let's say the current flowing over here will be I1 like this in this direction. Okay, let's can start with node number 2. Current flowing over here will be outgoing. That will be I2. Can I show the current direction between V2 and V3? No. So yeah, you guessed it right. It's a supernode. So node number 2 and 3 forms a supernode. Can I show the current direction between V1 and ground? No, because we have a voltage source connected. So we cannot show the current over here. We can show the current over here as, let's say, I4. Okay, let me write it as I4, and current flowing over here as I3 from year to year. Okay, now as we have seen before, what will be the value of if there is a voltage source connected between a node and the ground directly, then what will be V1? V1 will be directly equal to 10 volt. Okay, got it. Now we can also write it further that node number 2 and 3 form a supernode. Okay, node number 2 and 3 form a supernode. So we write the node voltages in terms of the supernode. So it will be V2 minus V3 is equal to 5. V2 minus V3 is equal to 5. All right, now we have two unknowns actually. V1 is already known, V2 and V3 we need to find out. So let's apply KCL at the supernode. So KCL at supernode. So this entire node, this node 2 and 3 behaves as a supernode now, and we have defined the current I2, I1, I2, I3 and I4 over there. So over here all are outgoing currents. So we can write I1 leaving the node 1, node 2, I2 leaving the node 2. Similarly, node 3, I4 and I3. So I3 plus I4 is equal to 0. Now what is I1? It's V2 minus V1 upon 2. I2 is V2 upon 8. I3 is V3 minus V1 upon 4. V3 minus V1 upon 4. And I4 is V3 upon 6 plus V3 upon 6, and that is equal to 0. Now what is V1? How much is V1? V1 is 10 volt. That is what we have got. Alright. So we substitute V1 as 10, and then let's rewrite these things again. Okay. So let me just mark here V1. Wherever we see V1, we write it as 10. Okay. So here we write it as V2 minus 10 upon 2 plus V2 upon 8 plus V3 minus 10 upon 4 plus V3 upon 6 is equal to 0. Alright, so let's dissect it further. This will be 0.5 V2 minus 5, 1 upon 8, it will be 0.125 V2. Here we'll get 1 upon 4 is 0.25 V3. 10 upon 4 will be how much? Okay, so it will be 2.5, and then plus V3 upon 6. So 1 upon 6 is 0.166 V3 is equal to 0. Now we club the terms together, and finally we write it as 0.625 V2. So we club the term V2 together, then V3 together, plus 0.4167 V3 is equal to 7.5. So this becomes our equation number 2. Alright. So yeah, that is enough to solve equation number 1 and 2 is enough to solve your V2 and V3, because there are only two unknowns now. So let me write it in the matrix form, and first let us write solve equation number 1 and 2. So we get, first let it write in a matrix form. So we have voltages V2 and V3. So V2 coefficient is 1, this is -1, and this is 5. Here it is 0.625 and this is 0.4167, and here we get it as 7.5. So please solve this in a calculator, and you will definitely get the answer V2 as 9.2 volt and V3 as 4.2 volt. Alright, please cross check these answers. Okay, and now we need to find the current flowing through all the resistors. Okay, so I1 is current flowing through 2 ohm, that will be V2 minus V1 upon 2. I2 will be current flowing through 8 ohm, that will be V2 upon 8. I3 will be current flowing through 4 ohm, that will be V3 minus V1 upon 4. And I4 will be um, current flowing through 6 ohm, that will be V3 upon 6. So let's write down one by one over here what we said. Okay, so I1 will be current flowing through 2 ohm, that will be V2 minus V1 upon 2. I2 will be I current flowing through 8 ohm, V2 upon 8. You can cross check this. I4 ohm will be I3, that will be V3 minus V1 upon 4, and I4 will be I6 ohm, that will be V3 upon 6. So let's check this out. This will be 9.2 minus 10. I mean V1 is 10 volt, so it is 10. So this comes out to be minus zero point 0.4 ampere, and the current direction is like this, I1. So you can see current direction this way from right to left. Okay, I of 8 ohm resistance will be 9.2 divided by 8, that will be 1.15 amperes, and the current direction will be I2, that will be going from top to bottom. Yeah, this is my current direction. Then I of 4 ohm will be V3, that will be 4.2 minus V1, that will be 10 divided by 4. This comes out to be minus 1.4 ampere, and the direction of I3 will be going from right to left. Okay, then I of 6 ohm resistance will be V3, that will be 4.2 divided by 6, that come out to be 0.7 amperes, and the direction of I4 will be from top to bottom. Alright, so these are all the currents which we were supposed to get, and yeah, that's it for today's lecture. And let's solve this in LTspice quickly and find out all the answers. So I'll open the LTspice window, open a new schematic, and let's build this circuit quickly. So I'll take the components and I'll type voltage. I require another voltage source over here. Now I'll connect all the resistors quickly. So here is my one resistor, and I have two resistors connected over here. One resistor connected over here. Let me join them together quickly with a wire. Okay, so this resistance is also connected. So automatically, as you can see, the node is formed over here whenever I connect with a wire. So there are three nodes, and there's the fourth is the reference node. I'll connect a ground to it with a wire. Okay, so this is my reference node. Now all the components are connected. Now I'll need to give the values. So this is 10 volt, this will be 5 volt, this will be 8 ohm, this is 2 ohm, this will be 4 ohm resistance, and this will be 6 ohm resistance. Alright, so all the values are well defined. Now we'll define the node numbers. This is node number 1, this was 2, and this was 3. Okay, let me rewrite as 2 and this as 3. So I'll label them node. Now this will be V1, V2 and V3. So we'll go to simulate, click on run, DC operating point, and click on OK. Once we get the value of V1 and V2 correct, so V1 came out to be 10, V2 came out to be 9.2, and V3 came out to be 4.2. So rest all the currents will be proper only. No, don't worry about it. All the currents will be in the proper manner. Okay, don't worry about the currents now. I of R4. R4 is 4 ohm resistance. 1.45. Yeah, it will be 1.45, zero point 0.4, 1.15, and 0.75. Okay, so in this answers, here it is 1.45. So 1 5 is missing. Um, let me write over here. So let me check with the calculator first. It is 4.5 minus 10 divided by 4. Yeah, it is 1.45, and in here it is, instead of this it is 0.75, I guess. 4.2 divided by 6. Yeah, it is zero point 0.7 only actually. Let us check this. Zero point 0.8 divided by 2, that will be zero point 0.4, and 9.2 divided by 8, that will be 1.15. So yeah, everything else is correct. So the current flowing through R4, I mean 4 ohm resistance will be I of R4. That will be minus 1.45, as we got it correctly. Okay, so this is correct. Then the current flowing through 6 ohm will be R2, so zero point 0.7. So this is 0.7 is correct. Then current flowing through 8 ohm resistance will be I of R1. That will be 1.15. That is also correct. And then current flowing through 2 ohm resistance will be I of R3, that will be minus zero point 0.4. So as you can see, all the values of currents are absolutely fine. These are the currents which we are looking for, and all are actually absolutely fine. Alright, so in this manner we can check any current or node voltages for a linear circuit consisting of resistors, voltage source and current source easily in LTspice, and we can cross check the values over here what we got it by analytical method. So this is all about nodal analysis. Now let's come to one last point about a number of equations which we solve. So let's go to this now, number of steps. Now at the end we are going to number of steps. So what did we do? We defined the ground on the reference node. Then we defined the other nodes and defined the variables on it, V1, V2, V3, to indicate the voltage at the other nodes. Then we applied KCL at each node to obtain the equations associated with it. And number of equations will be number of nodes minus 1. Let's check it out. So over here in numerical number 1, the number of nodes are 3 and the equations were 2. Okay, so yeah, that's it. So number of equations will be number of nodes minus 1. So there were 3 nodes and we were 2 equations. So that means for an n node circuit, there are n minus 1 node voltages, and we need n minus 1 linearly independent equations to determine these node voltages. Now one more thing we learned was, if a voltage source is connected between a node and a ground, as in this case, the voltage at the node is equal to the voltage of the source. So here V1 is 6 volt and V4 is minus 4 volt with respect to ground, of course. And if a voltage source is connected between the two nodes, we employ supernode concept. So here voltage source is connected between node 2 and 3. So 2 and 3 forms a supernode. So what do? We write the equation of the supernode using KCL. Okay. And then we write the equation relating the node voltages and the voltage source. Alright. So we formulate the remaining node equations by employing the KCL. So that we have seen now. So node 2 and 3 forms a supernode, and this is the equation relating the node voltages at the supernode. V3 minus V2 is equal to 12. Okay, and we have solved 4 numericals. One numerical was for home assignment, and we have seen 2 examples of a supernode. I guess this much is sufficient for you all to work on the nodal analysis and proper application of KCL. All right, so that's all for today. Thank you all for joining. If you have any doubts, you can post the queries in the comment section. So that's all for today. Thank you.